Okay, so welcome to this talk about applications of nonlinear photonics. I was thinking that now that you've been given the theoretical background and the computational methods, the simulation tools, you'd be eager to know about how this is applied in devices and instruments. Though I have to admit that partly this topic has been covered already by the previous talks, but I have quite a lot of content to add to this. And before we get started, I would like you to have a look at the list of nonlinear optical effects that I could come up with that have technical applications. And so you see there are a lot of them. There are things like optical rectification, optical parametric amplification, self-focusing, nonlinear polarization evolution. And so it becomes clear that this talk cannot be exhaustive. All I can do is that I can select a few applications that might be interesting for you, considering your background and your field of work. And in some areas I also don't have much time to go into depth, but you are free to ask questions after the talk if you need some more information. This has also been covered already, but I would like to talk more about it. Photonic crystal fibers. This is a very versatile platform for nonlinear optics, and it's also very prevalent in technical applications. These are so-called solid core fibers. They have a solid glass core in there which is surrounded by a hole pattern. And to understand the guiding mechanism in these fibers, it's enough to consider that the light will see the refractive index of the solid glass core in the center, and in the whole structure it will see the average refractive index over the air and the glass. So you can model this as a step index fiber. And the air filling fraction in the hole pattern, this gives us control over the index step. And this gives us a very strong handle effect on the index step, and it allows us to add a lot of waveguide dispersion to the material dispersion, and it also allows us to have very strong mode confinement here. And this helps to enhance nonlinear effects, to enhance the nonlinear coefficient. And we have more design parameters than just the air filling fraction. We can also vary the size and the geometry of the core. For example, here we have two cores next to one another, which will make the guided mode elliptic. We can have a similar effect by making some of the holes smaller, or to slightly distort this hole pattern, which has a similar effect. And this will have an influence on dispersion, but most of all, it will make the fiber polarization maintaining. It will make it birefringent, so the two polarizations will see different refractive index, and therefore, when you bend the fiber, when you curl it up, you induce stress birefringence, but this induced birefringence will always be weaker than the intrinsic birefringence that comes from the geometry of the core, and so you're unable to alter the polarization state, and the polarization will be preserved under any circumstances. And the main application for these fibers is supercontinuum generation. If you take it to an extreme and go to an extremely high air filling fraction, then you end up with something like this, a suspended core fiber where the core is suspended only on a few silica strands. There are people who call this a Mercedes fiber. You can probably imagine why. But this is not commonly referred to as a PCF because it lacks the periodic hole structure. So it's not a photonic crystal, but it allows extremely high mode confinement, which makes it very interesting for supercontinuum generation applications. On the other end of the spectrum, that is, if we go to very low air filling fraction, we can construct something that's called an endlessly single mode fiber. In this type of fiber will be single mode for all wavelengths that are being guided in the core. And this is different for a normal step index fiber. A step index fiber will be single mode only over a certain wavelength range, and then when you go to shorter wavelengths, it will become multimode. Here, this is not the case for geometrical reasons, as explained in this little sketch down here. So the fundamental mode is nicely enclosed in this by holes, but the first higher order mode has two antinodes which are small enough to fit in between those holes and escape from the core, and that will make it single mode. And these fibers are very convenient when you want to guide a very broadband supercontinuum and you nicely want to preserve the beam shape, the beam profile. And so the fact that we can make PCFs endlessly single mode allows us to construct something that is called a large mode area fiber. Here's an example. And the basic principle of that is that we can blow up the whole structure, we can make it really large, and it will still be more or less single mode. And this will also enlarge the mode profile of the guided mode, which it decreases the intensity and therefore avoids nonlinear effects. And yes, you heard that right. Sometimes when you engineer nonlinear interaction, your job is not to create nonlinearity, but to avoid nonlinearity or to avoid certain types of nonlinear effects. And for a CW laser, this is often stimulated Brillouin scattering. A stimulated Brillouin scattering is the dominant nonlinear effects for very narrow band sources. And it's very similar to stimulated Raman scattering. It creates phonons, but in this case, not optical phonons. It will create acoustic phonons. And these acoustic waves that you generate there, those are traveling density waves, and they have the inconvenient property that they reflect the light that creates it. So the more you go up with the power, the more stimulated Brillouin scattering you have, the more light gets reflected, so less and less light is coming out on the other side. And at some point, you get everything back. And this is very disturbing, for example, in CW lasers, and large mode area fibers help to reduce this problem. And this is used, for example, in high power amplifiers. As you can see here, the PCF structure is surrounded by another air cladding which guides the pump light. And the low air filling fraction here in this hole pattern allows the pump light to penetrate into the core and to pump it. And this allows nowadays to go to CW output powers of up to 20 kilowatts. These are really powerful fiber laser systems that allow to cut really thick layers of steel, that allow for drilling, welding, and so on. These are really powerful machining tools. A large mode area fiber is also used in pulsed amplifiers to avoid cell phase modulation. And this is applied, for example, in micromachining. Okay, let's talk a little bit about hollow core photonic crystal fibers. There are two types. One is the photonic band gap PCF, and the other one is the Kagome PCF. And in a step index model, it's impossible to understand why these structures guide any light at all. For the photonic band gap fiber, the explanation is the photonic band gap effect. And here, the whole structure that surrounds this hollow core acts as a Bragg reflector. It reflects the light and therefore keeps it confined to the core. This allows for a relatively low guiding loss, but only over a narrow spectral range, unfortunately. This is different for the Kagome fiber. You see the structure is also different. You have this repeating star shape by these interleaved triangles. The Japanese call this pattern a Kagome pattern, and this is where the name comes from. And to the best of my knowledge, it's not fully understood why this structure guides light at all, but it's not the photonic band gap effect, and the properties are also different. The guiding is more broadband, but also more lossy. And these hollow core PCFs, they have unique properties. They have a very high damage threshold. They minimize nonlinearity. They have very low group velocity dispersion because you have very little material. And they have good transmission, even at wavelengths where the glass absorbs. And this makes them very interesting for a variety of applications. For example, you can fill this hollow core with gases, and then you can do supercontinuum generation in gas. And this allows you to make a supercontinuum generation that reaches down to the extreme UV wavelength range. And such systems are already commercially available, and they can be used, for example, for extreme UV lithography. They can be used for spectroscopy, say spectroscopy of ions, where you need really high photon energy. And you can go even further. You can do high harmonic generation in these gas-filled hollow core fibers, and this allows you to go down to the soft X-ray wavelength range. And besides lithography and spectroscopy, this can be used, for example, to replace a synchrotron source or it can, high harmonic generation also allows the generation of attosecond pulses, of extremely short pulses. These fibers are also applied for dispersion-free delivery of ultra-short pulses. So when you have a femtosecond pulse and you guide it through this fiber, it will not experience much dispersion, which is, for example, applied in eye surgery. And it's also potentially very, very interesting for telecom applications. Number one, because it has very low nonlinearity and high damage threshold, so you can go in with a lot higher power and you don't need so many amplifiers. And the low group velocity dispersion is also very, very nice property here. And your signal travels at the speed of light in vacuum, not at the speed of light in glass, and this makes the signal transmission faster, so you gain a speed advantage. Unfortunately, these fibers have a guiding loss which is too high for telecom applications. But there are people who work on this, and once that they are successful, I believe that there will be a lot of people who would be willing to pay a lot of money to have a telecom network based on this and gain a speed advantage in this way. Okay, now I would like to talk about how these fibers are applied in incoherent supercontinuum generation. We've heard quite a bit about this already, but I would recap that. First, I would like to stress that from here I assume anomalous group velocity dispersion. Under normal group velocity dispersion, we will not experience any of the effects that I'm explaining now, but we will also have a very hard time to generate broad spectra or to easily get supercontinuum generation. The nanosecond and picosecond pulse regime is dominated by modulation instability. We get into this regime when our pulses are longer than 300 femtoseconds. I would like to recap some of the things that you should know already. So just like in a vacuum with the Maxwell's equations, in a nonlinear medium, for the generalized nonlinear Schrödinger equations, plane waves are a solution, okay? You can have propagation of plane waves. But the difference is that in this case, plane waves are not a stable solution. This is an unstable solution. And the slightest deviation from a constant CW wave will grow. So the deviation will grow more and more until the CW wave breaks apart into a train of pulses. And this happens randomly. Okay, the process is ultimately triggered by noise, either by shot noise or by amplified spontaneous emission, if you have this, which both have a quantum mechanical origin, and this is therefore perfectly randomized. And I always like to compare this in a mechanical analogy to the Rayleigh-Taylor instability. Imagine that you have a container that is filled with oil at the bottom and water on the top. Now the oil wants to come on top, but if you have a perfectly plane interface, it will remain like this because the oil doesn't know where to go up. But once you have the slightest deviation in this planar interface, the oil will come up there, bubbles will form, and the dynamic will become increasingly chaotic. And this is what we have in the case of modulation instability as well. Here I would like to show you an example. This is an X-frog trace. This is a representation in a diagram of wavelength versus time. And in this diagram, the vertical projection gives you the pulse envelope in the time domain, and the horizontal projection gives you the spectrum. And now let's see how this pulse evolves when it propagates along a nonlinear fiber. So you see that it decays into many, many subpulses. This happens by modulation instability. And in the time domain, the pulse is completely torn apart into countless little subpulses, and the spectrum is just wildly modulated. And this will be, the outcome is completely unpredictable. It's just random. And therefore, lasers or systems that are driven by this create extremely smooth, broad spectra. Why? This might surprise you, but because the spectrum that you've just seen didn't look smooth at all. It was wildly structured. But the point is that the structure is different for every pulse. If you have a very long pulse train with many pulses, then every pulse will have a different spectrum, and this will average to something very, very smooth because the spectral modulation is perfectly random. So it will average to something very smooth. You can see this here. This is an example of a incoherent supercontinuum output as compared to some other sources. And so the result is you still have perfect spatial coherence. You have a nice single mode laser beam, but extremely low temporal coherence. So you have the spectrum of a lamp. Compare this to an incandescent lamp, it looks more or less the same. But you have a lot more power density in the supercontinuum because you have a nice beam, which is not the case for a lamp, and so you get a lot more power into your spectrometer. If we compare this to other beam-like sources such as superluminescent diodes or ASE sources, then these ones also have high power density, but they are by far not as broad. And this makes this supercontinuum source unique and very interesting for applications. Usually such sources, they rely on microchip lasers, neodymium based at 1064 nanometers, which emit nanosecond pulses, and this is then followed by at least a few meters of PCF and maybe also a fiber amplifier before that. And such systems are available from a variety of different manufacturers, full system ready to use, and there are many applications for it. You can probably think about some of those applications. For example, this is a perfect source for broadband spectroscopy. When you want to send this through an absorption cell and do spectroscopy afterwards, either in transmission or you look at the photoluminescence, the fluorescence, or you do time-resolved measurements, this is a perfect source. It can also be used for microscopy, or mostly for confocal microscopy. This is where you focus your beam into a microscopy sample, and then you scan the focus over it, and you look at the fluorescence that comes out of the focal volume. And this gives you a 3D image of your microscopic sample with very high resolution, and there are even super resolution schemes that have a resolution that is lower than the wavelength of light. It can also be used for white light interferometry. In this application, you characterize the dispersion of optical components in an interferometric setup. You can characterize fibers, waveguides, mirrors for their dispersion properties. And it's also applied in biomedical imaging, for example, in optical coherence tomography. And this is something that I would like to explain on the next slide. So in this technique, we call it OCT, you split up the broadband light beam into two arms. One is the reference arm with a mirror, and the other one is the sample arm where you have a sample that you want to image, and you use this as a reflector. And then you recombine these two pulses and measure the output on a detector. Now, it's absolutely crucial here that you understand that you will see interference between these two arms only if the two arms are roughly at the same length within the coherence length of the light used. And if we have a really broadband supercontinuum source, then this coherence length is extremely short. It can be shorter than a micrometer. So these lengths, in order to see an interference pattern here, must be at the same length at less than a micrometer. But the sample might consist of several layers. So at several interfaces, you might see reflection, and therefore you might see the interference pattern several times. So by scanning the mirror along the beam, you can collect depth information here. And you can also collect the other spatial information in XY direction by scanning the beam across the sample, and therefore you get a 3D tomographic image of your sample. There are schemes here that don't rely on a movable mirror, and they allow for very fast acquisition times. And this is being used in ophthalmology for imaging of the back of the eye, mostly the retina and the macula. And this is being used every day in clinics and practices by eye specialists. This is an example for a technique that made it out of the laboratory into the clinics, where it makes a huge difference every day. Though, to be fair, many of these OCT systems, they rely on superluminescent diodes instead of supercontinuum sources, and you can see the difference in the resolution. Like I said, the resolution depends on the coherence length, and SLEDs just don't have such a short coherence length, and this is why the axial resolution is much worse when you have a superluminescent diode as compared to a supercontinuum source. So you can gain a huge advantage by going to a supercontinuum source here. Okay, let's now talk about the opposite. Let's talk about coherent supercontinuum generation. Again, we assume anomalous dispersion here. And we enter into this femtosecond regime where we have coherent supercontinuum generation when the pump pulses are shorter than 300 femtoseconds, which avoids modulation instability. In this case, the pulse evolves into a higher order soliton, which then breaks apart into fundamental solitons. And here's an example of this, of what this might look like. And I quickly want to remind you of these higher order soliton states. So a second order soliton is a pulse that breathes in width. A third order soliton is a double pulse where the two subpulses oscillate relative to one another. And a third order soliton is with three pulses that oscillate, and so on. But these higher order solitons, they are stable only on paper or in the computer model. They are not stable in reality because any effects such as higher order dispersion or stimulated Raman scattering will make them unstable, and they will break up into subpulses. And this is exactly what happens here. But the point is that this soliton breakup is not triggered by noise. The outcome is completely predictable and repeatable, and therefore there's no excessive noise generation, there's no chaotic behavior, and therefore the coherence is also preserved. And this is being used in broadening of frequency combs. Now, I know this has been covered already, but it's so important that I would like to repeat this. Frequency comb is generated by a laser that emits a train of ultra-short laser pulses. And now this pulse train is periodic, and when you Fourier transform this time domain representation, you go into the frequency domain where you see the spectrum of this pulse train. And since the pulse train is periodic in time, the Fourier transform will also be periodic with the inverse period. So these lines, the spectral lines that you get, are separated by the inverse time between the two pulses. That's the pulse repetition rate. Now, when you extend this, and by the way, if your pulse train is infinitely long, then the lines would be infinitely narrow. This would be a delta shape. But in reality, the lines are given as finite width by noise mechanisms. So if you extend this line pattern now to a frequency of 0, you don't end up at 0 exactly, but you have a slight offset. The whole pattern has a slight offset to 0. We call this the offset frequency. And we find this again in the time domain image by looking at the phase of the carrier wave relative to the envelope. So let's say we start with a phase delay of 0, then in the next pulse we might have a phase delay of delta phi, and then 2 delta phi, 3 delta phi, and so on. And this corresponds to a frequency, the offset frequency. And this comes from dispersion that you have inside of the laser cavity that generates the pulse train. And now if you send this pulse train into a nonlinear fiber, then you will broaden the spectrum and thereby progressively add more comb lines to your comb spectrum. And you might wonder, why is it that we remain on this grid? Why do we extend this comb structure? And you can think about this in several ways. For example, if you have a nonlinear interaction on this pulse train, then the nonlinear interaction will certainly not change the pulse repetition rate, will it? So it can also not change the line spacing. You can also think about it in other terms. The spectral broadening mechanisms such as cell phase modulation, dispersive wave generation, so on, these are all four-wave mixing processes. So you take the frequencies of 2 photons and make 2 other frequencies out of it. And if this process is seeded, then 3 of those frequencies are given, and so the 4th frequency is also given. So the fact that you stay on this frequency grid, you could see this as a consequence of conservation of energy. But that is not to say that the incoherent case is not possible as well. So if your pulses are too long, if they are longer than 300 femtoseconds, then you will not get a comb at the output of your PCF. You will get incoherent broadening, where the comb pattern disappears and everything is dissolved in noise. And by the way, the envelope of your supercontinuum that will then also be very smooth. And if you see such smooth spectra for a frequency comb, you should be kind of skeptical. It might be that you have a loss of coherence in there. And you can, as in the time domain image, you can think of it as phase noise. Okay, so this phase delay of delta phi, 2 delta phi, 3 delta phi, and so on will not be there anymore, and it will be replaced by noise. So the carrier wave will be extremely noisy due to the effect of modulation instability. And it can be shown that a pulse train of randomly phased pulses will not contain any comb lines. So if you want to broaden this, you make sure that you are in the femtosecond regime, and you will keep your comb pattern. And the envelope will be relatively structured as well. And there's another point that I would like to make here, namely, we call this supercontinuum generation, right? But actually, this is a misnomer here, because it's not a continuum. It's not continuous. It consists of discrete lines. So why do we call it a supercontinuum? And this is why some people prefer the term spectral broadening when we talk about frequency combs. But in fact, supercontinuum is perfectly fine, and this is a term that is used here, so it's also correct. Spectral broadening in frequency combs is very important for the technique of self-referencing. And for this, we need to broaden our frequency comb to an octave, so we can take the long wavelength end and frequency double it, and then overlap it with the long wavelength end. One thing I would like to mention here, to be really correct, is that what we call frequency doubling or second harmonic generation here is actually mostly some frequency mixing between those lines. This is why you don't double the repetition rate. But it's easier if you think of it as frequency doubling. So if you double the frequency of your comb lines, if you double those frequencies, you double all frequencies, including the offset frequency. If you take this equation times 2, then you end up with a comb that has twice the offset frequency, and therefore it generates a frequency comb with a different offset frequency that is shifted relative to the old frequency comb by exactly the offset frequency. And if you now take the interference, you record the beat node, then the frequency of your beat node will be exactly at the offset frequency. And for this, you need an octave spanning spectrum, and then you can build this so-called F-to-2F interferometer. And the offset frequency can thereby be measured, and the repetition rate can also be measured. That's quite simple. You just detect the pulse train on a photodiode. And these two frequencies are radio frequencies, and they can be counted using frequency counters. And if you can control them, you can stabilize those frequencies to another radio frequency, for example, from an atomic clock. And this, as a result, this means that all optical frequencies in your comb will be known with the accuracy and the precision of the atomic clock. So, and this represents an extremely precise measurement tool. But how do we use it? So how do we measure frequencies with that? So imagine that you have a CW laser of unknown frequency, and you want to use a comb to measure its frequency. Then what you do is you make it interfere with the comb, and then measure the frequency of the beat node that you observe. And this beat node will also be in the radio frequency range, just like the offset frequency and the repetition rate, and they can be counted. And then you can quite easily calculate the frequency of your CW laser if you know the mode number as well. So you need to know with which of those comb lines you are recording the beat with. But this is also easier to do, because with a coherence wavelength measurement, you can estimate which is the most nearby comb line. And you can think of the frequency comb as a ruler in optical frequency space, where the markings on the ruler are the lines of the frequency comb. Because how do we measure something, the length of something, then when we have a ruler? You take the ruler and you you put it on top of the thing that you want to measure, and the end of that thing, you compare it to the most nearby marking and check the position. And it's as easy as that, with the difference that this is incredibly precise. So if you stabilize your frequency comb to the cesium atomic clock, then you are using the very definition of the second. In the old SI system, the second was the most precisely defined frequency of the most precisely defined unit of all. So I think 1.5 years ago, the SI system was redefined, but before that, the second was the most precisely defined unit. And so you cannot be more precise than this, because the units are not defined more precisely. So the most precise measurements that have ever been made have used the frequency comb. This is Professor Hensch, the inventor of the frequency comb, and for this invention he received the Nobel Prize in 2005, along with these other two gentlemen, especially with John Hall, who also worked on frequency combs. And at the Max Planck Institute of Quantum Optics, around the year 2000, they developed the first frequency comb, and with that they could measure the 1s-2s transition in atomic hydrogen with 15 digits, with 15 significant digits. So with a tremendous accuracy, and this was a huge leap in terms of accuracy, and this made the theory of quantum electrodynamics the most precisely validated scientific theories of all. And this was in part possible due to the PCF. You can see it here, and here's the supercontinuum. And there's a nice anecdote about it, because the PCF was invented just a little bit earlier. And at MPQ, it was invented by Professor Russell at the University of Bath, and he gave a sample to MPQ. It was just a meter. They just had a single meter of PCF. And this was, for them, it was the holy grail, okay? They watched this fiber like a hawk, and it was more or less the most valuable thing that they had in the whole institute. There are more ways to stabilize the offset frequency using nonlinear effects. For example, you can take two subcombs and you can generate the difference frequency. And this will remove the offset frequency, okay? If you take these two subcombs with F0 offset frequency and you subtract that, then the offset frequency will cancel and you get a new comb that has no offset frequency. And this is worthwhile remembering that frequency doubling and some frequency generation double the offset frequency, but difference frequency generation cancels the offset frequency. And for this, you don't need an octave spanning spectrum. And in fact, if your spectrum is not that broad, this is a very convenient way of reaching very long wavelengths, of reaching mid-infrared wavelengths and stabilize the offset frequency at the same time. There is another method where you have frequency comb that propagates in a nonlinear fiber as a soliton. And as it propagates, it will be exposed to stimulated Raman scattering and the spectrum will be shifted more and more to longer wavelengths as the soliton propagates. So basically that's based on the soliton self-frequency shift that is caused by cascaded stimulated Raman scattering. However, one has to be careful with this because this compromises the coherence of the comb. Because there will also be some unseeded Raman scattering, which adds incoherent contributions to it. So you cannot easily go to very long wavelengths without losing some of the coherence. Okay, I would like to talk about a few frequency comb applications. And one of them is the optical atomic clock. Here you stabilize a laser to an optical atomic transition, and then you use a frequency comb to convert this optical signal to an electronic signal. Traditional microwave clocks, such as cesium and rubidium clocks, they reach 10 to the minus 16 fractional uncertainty, which is pretty good, but optical transitions are better because they oscillate at a higher rate. And so they slice time into smaller chunks, which makes it more precise. And with that, you can reach 10 to the minus 18 precision. And this is an absolutely overwhelming precision. And in order to give you an impression what that means, if you had two such clocks and you lifted one of them by just 2 centimeters, you would see that the two clocks would tick at a different rate because of general relativity. Okay, one of them is higher in the gravitational potential by 2 centimeters, and you can measure that already the time is ticking at a different rate then. So that's absolutely mind-blowing, and there have been discussions about redefining the SI second based on an optical clock. But the technology is not yet ready for this because they are still evaluating different concepts that either use trapped ions or optical lattices. And here the frequency comb is used as a clockwork, so to say. So you have this optical frequency, and you record the interference with the frequency comb, you record the beat node, and this will then be in the radio frequency range, which is accessible to electronics. So the frequency comb converts the optical signal to an electronic signal. You can also do the opposite. You can use a microwave clock, a cesium clock, rubidium clock, and use the frequency comb to transfer it into the optical wavelength range. Why would you want to do it? Because an optical frequency, or say a laser, erbium laser, can easily be transmitted through a telecom network. And this is what they are doing nowadays. So different countries have different atomic clocks, like the PDB in Germany defines the German time of day, and the CERT in Paris does the same thing for France with their atomic clock. And you can link the two over a telecom network, and so they can synchronize their clocks, they can compare them. And nowadays there are a whole lot of institutes all over Europe which get connected via telecom fiber and in order to establish a common standard and compare their atomic clocks. Another application, dual-comb ranging, and please forgive me that I don't explain dual-comb spectroscopy, which is very important as well, but I will explain dual-comb ranging. And here's how it works. You have two frequency combs that have slightly different repetition frequency. And the first frequency comb is split up in a Michelson interferometer with a reference arm and a measurement arm. And the task here is to measure the difference in length between the reference and the measurement arm. And you do this by recombining the two beams again and beating it with a second frequency comb with slightly detuned repetition rate. And you can understand how this works best in the time domain. But before I explain this, I would like to mention that there are two ways. Before that, there were two ways to measure distance with laser ranging. One is the time of flight technique, where you have a short pulse and wait how long it takes until this pulse comes back. This gives you an absolute distance, but it's not terribly precise. On the other hand, there are interferometric length measurements, which give you sub-wavelength precision, but it's not an absolute distance measurement because you can be off by a multiple integer of that wavelength. This technique combines both. Here you have an absolute distance measurement, which at the same time has interferometric precision, which has sub-wavelength precision. And you can understand this in the time domain by considering that the first frequency comb will emit double pulses after going through this Michelson interferometer. So you have a train of double pulses. Well, the second frequency comb has a single pulse, but it has a slightly different rate. So it will slowly, very slowly, overtake this double pulse. So the second, after each repetition, the blue pulse will be at a different point in time than the red pulses, and will scan across this double pulse. It will first scan across the first pulse, which will create an interference pattern, interferogram. And then after some time, it will reach the second pulse, where you have another interferogram. And the distance between these two recordings, it gives you the time of flight measurement. So here is the absolute distance. While these interferograms, they also have interference fringes, and this gives you the interferometric length measurement. And in combination, you have both. you have an absolute distance measurement with sub-wavelength precision. And the nice thing here is that you are using the definition of the meter. Why? Because the meter is defined via the speed of light, and here you have you measure the time that it takes for your light to pass that distance. So you measure it by using the speed of light, and this, for defining the speed of light, you also need a definition for the second. And if you log this to a cesium clock, you are also using that. So you use the definition of your units, of the meter. And another very nice thing that we are doing here is that we transform the measurement of a length into a frequency measurement. And that's great, because there is this famous saying by Arthur Shevlov, who was the former advisor of Professor Hensch at Stanford University. He famously said, never measure anything but frequency. And what he means by that is that frequencies are the thing that we can measure most precisely. We cannot very precisely measure a weight or a force or an angle. But if you can manage to turn this measurement of this other thing into a frequency measurement, then you win. Because frequencies are what we can measure most precisely, and then you can measure this other quantity with the same precision. And that's what we're doing here, and this is why we have really great precision in such measurements. I would like to end this talk by presenting a bit of an exotic application. It's the hunt for extrasolar planets, Earth-like extrasolar planets. And at first I would like to remind you of what I just said. You should never measure anything but frequency, and if you want to measure something else, you should turn it into a frequency measurement. And that's exactly what we're doing here. Here we're measuring an acceleration and turn this into a frequency measurement. So listen how this works. Imagine that you have a star other than the sun and a planet in its orbit. Now it's important to keep in mind that you cannot see the planet. The planet is far too faint and is far too close to its overly bright host star. You can only see the star, but the star will move a little bit because of that planet, because actually both the planet and the star are both in an orbit around their common center of gravity. So if you observe that star from Earth, you will see it coming towards the observer and then away from the observer, which creates a periodic Doppler shift in the Fraunhofer lines of the stellar spectrum. By the way, this technique just received the Nobel Prize last year to Meyer and Quilos for using it in finding the first planet outside of our solar system. And this method is still very important, is still very productive today. It has found hot Jupiters, super-Earths, and Earth-like planets. And for an Earth-like planet around a Sun-like star, you will get a radial velocity variation. So the radial velocity is the velocity component along the line of sight, a modulation of 9 centimeters per second, with a 1-year period, obviously. And to give you an impression of how little this is in terms of frequency, this is a fractional shift of 3 times 10 to the minus 11. So actually, if you, from the perspective of a frequency comb, this is a minor challenge, actually. I've just talked about 10 to the minus 16, 10 to the minus 18, so 10 to the minus 11 should easily be feasible, right? But if you think about it, what this means for astronomers, so they record the spectrum using a spectrometer with an image sensor, and there the lines would move by about 100,000th of a pixel. This is about the size of a silicon atom on this image sensor. And so it's very hard to detect this. There's very little detuning, very small detuning, and therefore we need to use frequency combs. Here is how this works, how you can use a frequency comb for that. So the telescope collects the light of a star and puts it into a nonlinear fiber, and the fiber, into a multimode fiber, sorry, and the fiber will be coupled to an Echelle spectrograph. That's basically a grating spectrograph with an Echelle grating. That's a ruled diffraction grating that works in very high diffraction orders. So you get many such diffraction orders, and they would be on top of each other if there wasn't the cross disperser, which is usually a prism or a grism that creates dispersion perpendicular to these Echelle orders and thereby separates the Echelle orders from one another. And then you get an Echellogram. So here you can see the spectrum. You can read the spectrum order by order, and here you can see the spectrum of a star with the Fraunhofer lines in it. But the shell spectrograph has a second channel, a second fiber channel that transports calibration source. And here it's the frequency comb. And you need this because such a shell spectrograph will drift. The alignment will inevitably drift, and you need to detect this drift in order to take it into account. And therefore, you need to calibrate your spectrometer simultaneously with every observation that you do. And if you want to use a frequency comb for this, you have two challenges. Number one, you need very wide line separation for this spectrometer to resolve it, which needs a very high repetition rate, a very high pulse repetition rate. And secondly, you need a really broadband spectrum to cover the full range of that spectrograph. And unfortunately, these two requirements are in conflict with one another. So when you have high pulse repetition rate, you have many pulses per time, so you distribute the available power among many pulses so that this leaves very little energy for each pulse. So you have a hard time to drive this nonlinear spectral broadening. And therefore, for spectral broadening, we use tapered PCF, which allows us to enhance the nonlinear interaction in the tapered fiber section. And in Menlo systems, we develop such frequency combs for astronomical applications, and we broaden them in tapered photonic crystal fiber. And we even built a little shell spectrometer for ourselves that we use in our laboratory. And here's how this looks in action when we project these shell spectrogram on a laboratory wall. And these little dots that you can see here, these are the comb lines of our frequency comb. And with this impression from our laboratory, I would like to conclude the talk and thank you for your attention.